In this lecture, we are going to talk about subatomic particles, atomic symbol and isotopes, and then about the average atomic mass. We've seen that early experiments led to the present day model of an atom. And now we know that atom has subatomic particles, namely the protons and neutrons, which are located at the center, and together they form the nucleus of an atom. And the electrons are outside the nucleus. But this picture of electrons buzzing around the nucleus in specific orbits, this is not correct. Electrons, they have both particle properties and they also behave like waves. That means two electron charges, electron densities, they can actually overlap with each other, just like waves can overlap with each other. So a better way to think is in terms of electron density or electron clouds, which is the spread of electron charge outside the nucleus. So a high density means you're more likely to find an electron in that region, and a low density means you're less likely to find an electron in that region. So you have to think in terms of these electron clouds outside the nucleus. Also, in this picture, the nucleus is not drawn to scale. The typical size of an atom is about 1 to 5 angstroms. That's the diameter. An angstrom is an angstrom. That's 10 to the negative 10 meters. So it's incredibly small. Atoms are incredibly small. And the nucleus is even smaller, at least 10,000 times smaller than the size of atoms. So to put this into perspective, if your atom is of the size of a football stadium, your nucleus would be the size of a pea at the center of the nucleus, center of the atom. And your electron would be the size of a grain of sand in the last row. It's far away from the nucleus. But it is easier to draw atoms with using this picture because we are able to see the particles clearly in this picture. So I'm going to use pictures like this, but remember these are not to scale, and also the electrons are not buzzing around like that. Okay, now what about the mass? The subatomic particles are not only just small, they're also very, very light. So we have to use very small units to describe their masses. So the AMU here is a very small unit. AMU stands for atomic mass unit. So one AMU is 1.6605 times 10 to the negative 27 kilograms. There are more decimals, but I just rounded it off to this point, this many decimals. But you can see this is 10 to the negative 27, meaning this mass is incredibly small. The mass of protons and neutrons are about 1 AMU. Neutron is slightly heavier. Actually, this is the heaviest subatomic particle. And electrons' mass is about 2,000 times less than proton and neutron. So it is very, very light. So only protons and neutrons contribute to the weight of an atom. All the mass is packed in the nucleus, so very tiny volume carrying a lot of mass. So we can say that the density of the nucleus is incredibly high. A lot of mass packed just inside a very tiny volume. Also, electrons, since they are very light, we can assume that removing electrons or adding electrons is not going to change the mass of an atom. Just like removing your ring is not going to change the weight when you're standing on a scale because it's very light compared to your body weight. So keep that in mind when you see pictures like this. You have to see electrons as not only just tiny, but also as very light, and they don't contribute to the weight of an atom. The weight is coming mostly from the nucleus, almost entirely, I should say, from the nucleus. Now coming to charge, charge is also small, so we use atomic mass units to represent the charge. So for charge, one atomic unit, I shouldn't say atomic mass unit, I should just say atomic unit. So one atomic unit of charge is 1.602 times 10 to the negative 19 coulombs. Okay, so proton is positively charged, and the charge is 1.602 times 10 to the negative 19 coulombs. Okay, and electron's charge is again 1 atomic unit, which is that much, but it's negatively charged. So it's important to know which ones are negative, which ones are positive, and which ones are neutral. A neutron went to the bar, and the bartender said, for you, no charge. Furthermore, an atomic symbol can be used to give us information about how many electrons, neutrons, and protons are there in an atom. So before we learn to write the atomic symbol, let's learn some terminology. Atomic number, represented by the uppercase Z. It's the number of protons in an atom. Mass number, it's represented by the capital letter A. I think in the US you call it uppercase. So yes, it's represented by the uppercase letter A, and it's the number of protons plus neutrons. Most students make an error saying atomic number is number of protons, and so mass number would be number of neutrons. No, think about it. The mass of an atom comes from both protons and neutrons in the nucleus. So mass number should be number of protons plus neutrons together. Okay, so now once you know these, how do you write an atomic symbol? You put the mass number on the top, the atomic number on the bottom, and on the right you put the element symbol. So for this atom, we can see there are 2 protons, the positively charged particles in the nucleus. So the atomic number would be 2. We have a total of 4 particles in the nucleus. So protons plus neutrons, so that's 2 plus 2, that's 4. So the mass number would be 4. Now what element is this? What should be the atomic element symbol here? Well, atoms are recognized by number of protons. Okay, so if you look at a periodic table, the number of protons, or in other words, the atomic number, is written on the top. So an atom with 6 protons would be carbon. An atom with 4 protons would be beryllium. An atom with 33 protons would be arsenic. That's how you recognize an element. So in this case, this atom has 2 protons. Its atomic number is 2. So our element is helium. So that will be our symbol. So this is your atomic symbol, and it gives you information about how many electrons, protons, and neutrons are there. We already said it contains 2 protons because the atomic number, which is number of protons, is 2. Now, what about the neutrons? How many neutrons do you have here? Can you predict that just looking at the atomic symbol? Well, you have a total of 4 protons plus neutrons, and you know out of these, 2 of them are protons. So you have to subtract the atomic number from the mass number to get the number of neutrons. So remember, number of neutrons is given by the mass number minus the atomic number. And here it's 4 minus 2, which is 2. So we have 2 neutrons. And what about the electrons? Furthermore, the atomic symbol, usually the charge is written, the electrical charge is written on the top. And if you don't see any charge, plus, minus, or 2 positive, 2 negative written there, it means the charge is 0. It's a neutral atom. And in a neutral atom, the positive charges and the negative charges, they balance, they're equal to each other. So since this atom is neutral, since we don't have any charge written on top of it, number of electrons should be equal to number of protons. So we have 2 electrons in this atom. Okay, let's write the symbol for this atom picture. Start with number of protons. You have 3 protons. Your atomic number is 3. So if you look at the periodic table, the element with 3 protons is lithium. So this would be a lithium atom. So I can write lithium. What about the mass number? That's protons plus neutrons together. So let's count. You have 3 protons, you have 4 neutrons, so that's total of 7. So the mass number is 7. Okay, so you can just leave it like that, or you can write the atomic number 3 at the bottom. You can leave this out because the lithium, the element symbol, is telling you what the atomic number is. So sometimes you don't see this written. It's just this is also correct. Some other times you will also see this referred to as lithium 7, giving you just the mass number. Okay, now if I take out one electron from this, think about it. Is this atom neutral? No, because you have 2 electrons and 3 protons. Your positive charge exceeds the negative charge. Okay, so you have one extra positive charge, so this gets a positive charge. This is no longer electrically neutral. So this is now called ion. It's no longer an atom. Any atom carrying a charge has no balance between the positive and negative particles. So it gets a charge, and we refer to this as an ion. So this would be a lithium 7,3 positive. So you can say lithium plus 7 ion with a positive charge. Okay, so how do we create positively charged ions? By removing electrons. So when electrons are removed from a neutral atom, it results in a positive charge, and the positively charged ion is referred to as cation. So sometimes I tell students to write the T as a plus, so you remember that cations are positively charged. Or another favorite line for a student is cats are positive. So cations are positively charged ions. Okay, now the key is to remember that you're not touching the protons. You're just removing or adding electrons to create ions. Okay, because basically in most chemical reactions, electrons can be easily removed or they can be added, not the protons. It's very difficult to change the number of protons. Those do happen in nuclear reactions, like for example, in a nuclear reactor that produces electricity. You have reactions going on that will change the number of protons, but not in the regular chemical reactions that we do in the lab. Because if you touch the nucleus, enormous amount of energy is released, or you also need enormous amount of energy to do that. Okay, so remember, when you create ions, you are just removing or adding electrons, not protons. All right, how about we add a proton add an electron this time. What would be the symbol now? So this would be lithium. The atomic number is 3. The mass number is 7 because we didn't change anything in the nucleus. Okay, but we have an extra negative charge now. So this would be lithium negative ion. Okay, and we call this an anion. Okay, so if you add another electron, then this would be lithium negative 2 or 2 negative. Okay, so when electrons are added to neutral atoms, it would result in negatively charged ions called anions. Anions are negative, cations are positive. You create them by either removing or adding electrons. If you remove electrons, you get a positively charged ion. If you add electrons, you get negatively charged ions. So here we have different versions of carbon atom. How do I know it's carbon atom? Just count the protons. You see you have 6 of them in each. They all have 6 protons, and since they're neutral, they also contain 6 neutrons. So we can say this element is carbon because if you look it up on the periodic table, um, the 6th element with 6 protons is carbon. What's the difference between them? They differ in the number of neutrons. The first one has a total of 6 neutrons. So its mass number, which is protons plus neutrons, is going to be 12. So this is carbon 12 isotope. Um, I use the word isotope. I'm going to explain just in a bit what that means. Um, the second one has a total of 7 neutrons. You can go ahead and count them. So the mass number will be 6 plus 7, which is 13. And the other one has 8 neutrons, so it's a carbon 14. So all these are different versions of carbon. We call them carbon isotopes. So what is an isotope? It is Isotopes are atoms of the same element, but they differ in their number of neutrons, and that's why their mass numbers also will be different. And since their mass numbers are different, the masses are also going to be different. Since this one has one extra neutron, it's going to be slightly heavier than this carbon, and this one is going to be further heavier. There's also another isotope of carbon, the carbon 11, but this one is synthetic. It does not occur in nature. This one is synthesized in the lab in nuclear reactions. The other ones occur in nature. The carbon 12 isotope accounts for about 98.89% of all carbon in the universe. So if you look at carbon in the universe, 98.89% of it, carbon, is made of carbon 12 isotope. And about 1.109% of carbon in the universe is carbon 13, and the rest, very tiny portion, less than a trillionth, you can say less than 0.0001%, is carbon 14. This carbon 14 isotope is actually radioactive. That means if you look at carbon 14 in a sample of carbon, eventually you're going to see this decay and convert to carbon 12. It's going to spontaneously decay. That's because there are too many neutrons that are pushed together into the nucleus. And because of that, this carbon 14 over time, it's going to give off neutrons and convert to the most stable form of carbon, which is carbon 12. Okay, so now that we know that every element comes in different versions with different number of neutrons, how do we calculate the mass? In other words, the average mass of carbon. So suppose you're weighing carbon, how do you know what the average carbon mass would be? So that's our next concept, average atomic mass. If you look at the periodic table and pay attention to the number on the bottom, this is mass of carbon, one carbon atom. And since we said carbon doesn't come in just one form, we have different isotopes or different versions of carbon. Whose weight is this? This number, 12.011, by the way, the unit is AMU, atomic mass unit, which is a small unit. This is the average atomic mass of carbon. It's not a simple average, it's a weighted average. It's a weighted average of all the carbon isotopes masses. So what is weighted average? I do this weighted average all the time when I calculate your grades. For example, instead of talking about grades first, let me give you a simple example of different element. So let's say you have two versions of an isotope X, one with a mass of 10 atomic mass units and another with a mass of 12 atomic mass units. So what is the average? What is the average atomic mass? Well, if you just have equal amounts, so let's say you have one of this and one of this, instead of writing the x's, let me just draw a blob so you can see clearly. So here's an atom with mass 10, here's another atom with mass 12. So if I have equal amounts of those, then it will be just 10 plus 12 divided by 2. That's going to be basically it's a average which is distributing the weight equally between those two. So the average is 11. Okay, so we took half of 10 and added half of 12. That will give us the average. Okay, What if you don't have equal quantities of each? Suppose you have two atoms with an average, mass 10 and three atoms with mass 12. Now, what is the average mass of this carbon in this sample? Okay, so in that case, your average here is going to be, you add up all these masses, so that's going to be 10 plus 10 plus 12 plus 12 plus 12. And now you divide it by, we have a total of 5, so divided by 5. Okay, this can be rewritten as 2 times 10 because you have two tens plus 3 times 12 divided by 5. Now we can distribute the denominator using algebra. So we can rewrite this further as 2 times 10 over 5. So it doesn't matter if I write over 5 like this or put the 5 under 2. So you can write this as 2/5 of 10 plus 3/5 of 12. Okay, so this is my average. Okay, so the average is 2/5 of the atom with mass 10 and 3/5 will be the mass 12. Okay, and you can see the logic here. Because the sample is made out of 2/5 of the sample is made out of 10, the average mass should be 2/5 of 10, should contain 2/5 of 10, and it should contain 3/5 mass of 12. Okay, 3/5 of the mass of the sample should be made out of 12. Okay, we can apply the same logic here. So when we deal with isotopes, instead of giving this simple fractions, you're dealing with billions and zillions of molecules here. Okay, so we have a percentage. This percentage can be thought of as a fraction. That means you have 98.89 out of 100 and 1.109 out of 100. This is the fraction of molecules that are made out of carbon-13, and this is the fraction of molecules that are made out of carbon-12 in the universe. So you take the fractions and multiply by the weights. The weight of carbon-12 is exactly 12. So it's 12.000 AMU. And the weight of carbon-13 is 13.003 AMU. So you multiply that. And then you would just add them up. So calculate this number, and add them. Okay, just like you did here. You took the weight and multiplied it by the abundance, so 2/5, and you took this weight and multiplied it by the abundance and added them up. Okay, so this number, you can put it in your calculator and calculate the answer. It should be equal to 12.001 AMU. You should get an answer pretty close to what is listed in the periodic table. And that's how you do average atomic masses. You take the fraction, you take this fraction is usually referred to as natural abundance, and multiplied with the weight. You do the same for every isotope. Take the fraction, multiplied by weight. Don't forget to convert the percentages into fractions. And then you add them all up, and that will give you the average atomic mass. And notice that the average is pretty close to the most abundant one, okay? Because most of the carbon in the universe is made out of carbon-12, the average should be pretty close to the most abundant isotope's mass, okay? And that's what you're seeing here, okay? All right, coming to a real-life example of um, average atomic mass. This is how I calculate your grades. So this is my abundance or the fraction, okay? So 20% of your total grade will be made out of the lab score, okay? So your final grade should contain 20% from the lab. So 20% means 20 divided by 100, which is 0.2 times 95, okay? And then I take 20% of your homework grade, and let's say this is not my syllabus, let's say another teacher is doing this, okay? Then you would take 60% of what you made on the exam, okay? If this is what her or his allocation is. And then next you would add them all up, and that should give you the weighted average.